Welcome, this is Dr. Chen, and today we're going to sketch a graph. We're going to do it, we have graphing calculators, but we're going to learn the techniques to do it without this. So the first thing we're going to do is kind of go over the steps quickly, and then do an example. If you want, we'll do a second example in another video, because they're long. So, the steps. I said it's long. There are a lot of steps to graphing, a lot of things that are important. The first thing, I put in parentheses because it's usually not at all important, but we have to consider the domain of the function. Some functions have restricted domains, like the square root of x, or natural log of x, and so forth. So just be aware of that, and then we'll move on. The next, we're going to find the intercepts, the y-intercepts, the x-intercepts. This is where it crosses an axis. And these are useful points because they help anchor your graph on the axes and tell what's going on. They're easy points, which is why we do them. They don't really have to do calculus, but they're easy points, so we should do them. Y-intercept, you just plug 0 into the function, and we're done. X-intercept, you figure out where the function is 0. These are the roots of the function. Then, we're going to look at the long-term behavior of the function. This is asymptotes. An asymptote is something you get close to. So a horizontal asymptote, the function is getting close to some value. A vertical asymptote, the function as it comes in gets close to some value, typically going up or going down. There are also oblique asymptotes. We'd write them as OA. And we're not going to worry about them as much, but if they come up, we'll deal with it. Then we're going to talk about where the function increases and decreasing. This is the really heavy calculus part. We take by finding critical points and making a number line. Find the derivative, find the critical points, and we mean the x, y values here because we're going to put them on a graph. It's good to know what the x and the y are. Then we're going to make a number line for f prime. Tells us where the function's going up, where the function's going down. And it also tells us mins and maxes, but that's sort of incidental to this. We're going to use that information, but we've already found them here. Next, we're going to talk about concavity, the second derivative. We're going to look for the candidates for inflection points. An inflection point is where the concavity changes sign from plus to minus or minus to plus. So it's important to know what those points are. And again, it's x, y points because we're going to graph them. Then we make a number line for the second derivative, noticing where it curves up, where it curves down, and so forth. There is one more step here. If there aren't enough points yet, we can add some. Usually that's more than enough to get a pretty good graph. But sometimes you need a few more. And then we put it all together. So let's try an example. I'm using a polynomial this time. X cubed minus 4x squared minus x plus 4. And I've already told you the domain is the real numbers. Why? Because you can plug any x in here and not get an error. It's, as I said, usually not important to worry about it, so I'm just mentioning it. The y-intercept, I plug 0 in for that. We get y equals f of 0, and I get 4. The x-intercept, I should put an s there because it can be more than one. There can only be one y-intercept for a function, but there can be many x-intercepts. And we solve for that 0. Now that's a cubic, and it's hard to solve cubics just directly. There's no cubic, well there is a cubic formula, but there's none that's standard for this level of mathematics. So what we do is we look for patterns. The coefficients, 1, minus 4, minus 1, 4. This is definitely a pattern. And when you see these kind of patterns, you should start thinking that there could be some simple values that might work. Try 1. 1 minus 4 is what? Minus 3. Minus 1 is minus 4 plus 4. It works. If 1 is a root for this, that means x minus 1 is. So you can go x minus 1, and then try to factor the rest. If you do, you're going to get, what are we going to get? X squared. We're going to get a minus 4 over here. And we'll probably get minus, let's see, there's minus 1x squared. We want to have minus 4x squareds total, so that's minus 3x squareds, or 3x. Does that work? Probably. But that also factors into x minus 1 times x plus 1 times x minus 4. So there are 3 here. The set will be 4, minus 1, and 1. We'll work on some more of those if that causes a problem. But right now, I want to look at the next step. As x goes to infinity or minus infinity, out this way, what happens? If we go towards infinity, only the top term makes a difference. So what do? We go towards infinity, it's going to be positive infinity. On the other side, as we go to minus infinity, again, the highest power term is the one that makes a difference. We get minus infinity. So far, this could have been something you learned in pre-calc. But now we're going to do something definitely calc-based. We're going to take the derivative. It's not a terrible derivative. Let's see, 3x squared. I don't know what the answers are going to be. Minus 8x minus 1. We need to know, is this ever 0? That's the critical points. Zeros or does not exist here. And again, it's a polynomial, so it does not exist is not an issue. So set this to 0. I can't do this one in my head, so I don't think it even factors. So I'm going to use the quadratic formula. X equals negative b plus or minus square root of b squared minus 4 times a times c all over 2a. I get 8 plus or minus, what's that, 12 square root of 76 all over 6. And I'm really actually more interested in a decimal approximation for these than I am in the actual algebraic answer to, or approximation for, or exactness for this. So I get 2.778 and 8 minus square root of 76 divided by 6 is negative 0.12. Those are the x values of the critical points. To get the y values, we plug them into our original function. So using the handy dandy table here, I get negative 8.209 or at negative 8.21 and positive 4.06. Okay, what are these values? These values are the values we put on the number line. Well, the x's are negative 0.12 and positive, and then positive 2.78. We're going to find the derivatives for these. So, I don't actually need to know, well, I know the derivative here is 0, the derivative here is 0. I need the regions. So I need a value in each region. Just choose a value, plug that into our derivative. Where is the derivative? Right here. For 0, that makes that negative. For 3, 3 times 3 times 3, 27 minus 24, that's going to be positive. And put a minus 1 in, well, that's positive. It's going to be more than those, it's positive. What does this tell us? It tells us we're going up, we're going down, and then we're going back up. That's the kind of graph we have. One last bit that we have to worry about is the second derivative. We take the derivative of the derivative, 6x minus 8. Again, that's never does not exist, so we set it equal to 0. X equals 4/3. And we also need the y value. So plug that back in our function. And we get minus 2.07. We're going to need to make a number line for the second derivative. 4/3 about 1.33. So f double prime, I need something over here, something over here. If I put 2 into the second derivative, I get positive. If I put a 0 in, I get negative. So the graph looks like this. We're going to put all of that together. That, the increasing, decreasing, the intercepts, and so forth. So when I draw this, I look for all the x values that are interesting. I have an x value of 4 that's interesting here, and a minus 1. I have, those are still in the same range, that's still in the same range. I really only need to go out to about 5 here, or 6. Probably even less here. As far as the y values, well, I've got a minus 8 here and a positive 4. So I'm going to plot this graph now. And just so I can be clear, I'm going to use a different color here. So, first of all, the y-intercept is 4. The x-intercepts are 4, minus 1, and 1. So 4, minus 1, and 1. The graph is already starting to form. What other interesting points do we have? At minus 0.12, we're at 4.6. So that's about minus, right about here and here, maybe? And why is that an interesting point? That is this point here. It's a max. Since I know that's a max, I kind of know the graph's going to do that. Then I have 2.78 minus 8.2. So 2.78 is about here. Minus 8.2 is about there. If you check, that's a minimum. So that's why I did that. One last point, we have this one right here. And when x is 1.3-ish, we get minus 2-ish. That, if you look at it, is a change in concavity. That's an inflection point. And then lastly, what else did we not use? We did not use this. As x goes to infinity, it goes up. As x goes to minus infinity, it goes down. So the graph's going to look like this. It's going to curve. This is concave up. And then this part is concave down. It's not a very complicated graph. It's a cubic. But hopefully, these methods will serve you well in any graph you do. Until next time, Dr. J.